You know how we're always hearing about AI doing amazing things these days? Writing stories, translating languages like it's no big deal.
It's pretty mind-blowing.
Right. Well, a lot of that started with this paper. It's simply called Attention is All You Need.
Catchy title.
Yeah, and the idea they introduce, self-attention, it's like the secret sauce behind some of the most powerful AI models out there like ChatGPT.
It's really foundational, yeah.
So that's what we're diving into today. But before we get all tangled up in the magic of self-attention,
Good idea.
let's set the stage a bit, right? We're talking about tasks like translation, summarizing text, things like that.
Yeah, classic natural language processing stuff.
Exactly. And traditionally, the way these were handled, it was very step by step.
Think of it like reading a sentence, but you could only look at one word at a time.
Okay, so one word, then the next, then the next. That sounds pretty slow.
Right. And these older models, they often use something called recurrent neural networks, or RNNs for short.
Mhm.
They kind of got bogged down by long sequences.
Like if you were trying to read a whole book but only one word at a time, you'd never finish.
Exactly. Inefficient, to say the least.
So that's where this transformer, the architecture from this paper, that's where it comes in, right?
Yeah.
It ditches that whole step-by-step thing, and it's all about attention.
That's the big idea.
Instead of one word, then the next, it's like the model can see the whole sentence at once.
That's a great way to put it.
Hmm.
The transformer considers all the words simultaneously.
Okay, that sounds way more powerful, but how does this attention actually work?
So at the heart of it is this mechanism they call scaled dot product attention.
Catchy, very catchy.
It's all about finding the most relevant information for the task at hand.
Kind of like when I'm searching for something online, right?
Think about it like this. You have a question, like a search query,
Okay, got it.
and you're trying to find the most relevant books in a library, say.
So the AI is doing the searching this time.
Exactly. And this query is matched against a set of keys.
Keys, like literal keys.
Not quite. Think of them like the titles of the books in our library.
So I'm looking for a specific book. I use my query to find the right key, which is the title.
And each key is associated with a value, which is like the content of the book itself.
Okay, I'm starting to see the analogy here.
So the AI sifts through all this information using the query and the keys.
And it picks out the values, the actual information that are most relevant.
That's it. And the clever part is it uses a weighting system.
A weighting system.
It figures out how important each piece of information is based on how well the query matches the keys.
The better the match, the more important that information is.
Precisely.
Okay, this is starting to sound like superpower territory, like the AI has this incredible focus.
It's powerful stuff.
But what if it needs to consider different perspectives? Does it just get tunnel vision?
Great question. And that brings us to multi-head attention, which is like having a team of experts, each with their own perspective.
Okay, like having multiple detectives on a case.
Perfect analogy. So instead of just one set of keys and values, we have multiple sets, all working in parallel.
And each one, each head, as they call it, focuses on a different aspect.
And that's key, right? It helps the model get a more well-rounded understanding, just like having different detectives looking at the same clues.
So it's not just one interpretation. It gets a richer, more complete picture.
Exactly. It avoids getting stuck on a single viewpoint, much more flexible.
Okay, so we've got this powerful attention. It can see the big picture, multiple perspectives. Now, how does this all fit into this transformer thing?
Ah, good transition. The transformer uses attention in three clever ways. We have encoder-decoder attention, encoder self-attention, and then decoder self-attention.
Okay, that's a lot of attention. Let's break it down. Where do we start?
Let's start with encoder-decoder attention. That's kind of the classic attention mechanism.
All right, classic, good place to start.
So you've got the encoder, which is responsible for understanding the input, like a sentence we want to translate. And then you have the decoder, which generates the output, the translated sentence.
Encoder understands, decoder generates, got it.
And the decoder uses this encoder-decoder attention to focus on the most relevant parts of what the encoder understood.
So it's like the encoder saying, hey, decoder, I found this important stuff. And the decoder saying, okay, thanks, I'll pay extra attention to that.
Exactly. It's a way for them to communicate, focus on the right information.
Okay, now what about this self-attention business? How does that work?
So encoder self-attention, this is where things get really interesting.
Lay it on me.
Here, each word in the input sentence, it actually looks at every other word in that sentence.
Like each word is analyzing the entire sentence on its own.
That's right. It's trying to understand its own context, its relationship to all the other words.
It's not just about the word itself, it's about its role in the sentence.
Precisely. And this is where the self comes in. It's attending to itself, to the other words, in its own sequence.
Wow, that's pretty deep. Like each word suddenly becomes aware of its surroundings.
It's about understanding connections.
Okay, now we've got encoder self-attention. What about on the decoder side?
Decoder self-attention works similarly, but this time it's happening on the output side.
So each word in the translated sentence.
It looks at all the previous words that have already been generated.
So it's like when we're writing, each new sentence we write builds on what's come before, make sure it all flows together.
That's it. Decoder self-attention helps ensure that the output is coherent, grammatically correct, all by keeping track of what's already been said.
Okay, I'm starting to see how this all fits together, but hold on, back up a second. Why is this self-attention such a big deal? What makes it better than the old way?
Ah, that's the million-dollar question.
$1 million question, exactly.
Well, there are three main reasons why self-attention is so impactful. First off, it's incredibly efficient.
Efficient. That's music to my ears.
Right. Unlike RNNs, which have to go step by step, self-attention can be parallelized, meaning it can process things much faster, especially for shorter sequences like sentences.
So it's like instead of doing things one at a time, it can do multiple things at once.
Exactly. Much more efficient.
Speed. I love it. Okay, what else?
Another key advantage is that self-attention is way better at capturing what we call long-range dependencies in language.
Long-range dependencies. Okay. Got to break that one down. What does that mean?
It's about understanding the relationships between words that might be far apart in a sentence.
Like if a pronoun refers to a noun that's way back at the beginning of the sentence.
Exactly. Think about the sentence. The cat sat on the mat, even though it was Gertie.
Okay. It refers to the cat, even though there are all those words in between.
Right. And RNNs, those older models, they often struggle with those kinds of relationships because they have to process one word at a time.
So they kind of lose track of the context as they go along.
But self-attention, it can see the whole sentence at once, so it easily grasps those long-distance connections.
It's like having a wider field of vision, right? It can see how everything fits together.
Perfect analogy.
Yeah.
And that's really important for tasks like understanding the meaning of a text or translating it accurately.
Where context is everything. Yeah.
Absolutely.
Okay, we've got speed, we've got context. What's the third reason?
The third reason is something that's really appealing, especially for those of us trying to understand how these AI models work.
Okay, I'm intrigued.
It's called interpretability.
Like being able to understand what the AI is thinking.
That's the idea. With self-attention, we can actually get a glimpse into the model's thought process.
So we can see what it's focusing on, how it's making decisions.
Exactly. By visualizing which parts of the input the model is paying attention to, we can kind of see what's important to it.
That's pretty amazing. It's like, imagine reading a text and being able to see which parts the AI highlighted as the most important.
Right. We get insights into its reasoning.
Okay, this is getting really cool. But I'm already feeling a bit overwhelmed. We've got attention, multi-head attention, 3 types of attention in the transformer.
It's a lot, I know.
It is, but it's fascinating.
And there's one more crucial detail we can't skip over. Positional encoding.
Okay, hit me with it.
Remember, we said that self-attention considers all words in the sentence simultaneously.
Yeah, it's like seeing the whole thing at once.
The problem is self-attention itself, it doesn't actually care about the order of the words.
Wait, hold on. That sounds like a big problem. Word order is kind of important, isn't it?
It is, and that's where positional encoding comes to the rescue.
The rescue good? We need that.
It's basically a way to give the model information about where each word is located in the sentence.
So it's like giving the AI a map of the sentence structure.
Exactly. And the authors, they use a very clever approach. They use sine and cosine functions to represent these positions.
Sine and cosine, like from trigonometry class.
Yep, that's the one. Yeah. Might seem surprising, but those functions, they're really effective for representing this kind of positional information.
So they're using math to encode the word order.
Exactly. And this lets the model understand not only the individual words, but also where they fit in the sentence, which can change the meaning completely.
Okay, so we've got self-attention that can see the whole sentence, multi-head attention from multiple perspectives, and now positional encoding for word order.
It's like we're building up the ultimate AI language toolkit.
It sounds like this transformer is a real game changer.
It is. And to see how well it actually performs, we need to talk about the results they got. And trust me, they're impressive.
Results, okay, lay them on me.
They trained the transformer on several different machine translation tasks, and it blew the previous state-of-the-art models out of the water.
Hold on. They built this brand new architecture based on this radical self-attention idea, and it actually worked.
It not only worked, it worked amazingly well, and they achieved these results in way less training time than some other models.
Okay, so it's faster and more accurate. That's pretty remarkable.
It's a big deal. And they didn't stop there. They also did all these experiments, tweaking different parts of the model, trying different variations.
So they weren't just satisfied with building something that worked. They wanted to really understand it, see how far they could push it.
Right, they wanted to know what makes the transformer tick.
They were tinkering under the hood, so to speak.
Exactly. And those experiments gave them a ton of valuable insights into how each piece of the transformer contributes to its overall performance.
Okay, so it's not just a black box. They actually have a pretty good understanding of what's going on inside.
They do.
Yeah.
And that's one of the things that makes this paper so important. It's not just about the results. It's about the understanding, the insights they gained along the way.
All right, so we've covered a lot of ground, self-attention, the transformer, how they trained it, the experiments.
We've just scratched the surface, but it's a good foundation.
It is, and I'm already excited to dive deeper. But for now, I think it's time for a break.
Sounds good to me. All right, you ready to get back into it?
Absolutely. I'm eager to learn more about, well, everything, really. Where should we go next?
Well, last time we talked about how the transformer works in theory, right? But now let's get into the nitty-gritty of how they actually trained these models.
Okay, yeah. Gotta teach the machine somehow.
Exactly. And that starts with the data they used, the fuel for the AI engine, so to speak. For translating English to German, they used something called the WMT 2014 dataset.
WMT, that's, gotta be some acronym, right?
Stands for Workshop on Machine Translation. It's a standard benchmark in the field. And this particular data set, it's massive. We're talking 4.5 million pairs of sentences.
Hold on, 4.5 million. That's like more sentences than I've spoken in my entire life.
Probably more than both of us combined. Each pair has one English sentence, and its equivalent in German. That's a lot for the model to chew on.
So they just feed all those sentences in raw, as is.
Not quite. There's a bit of pre-processing involved. They use a technique called byte pair encoding.
Byte pair, okay. Another jargon term. Got to decode that one.
It's not as complicated as it sounds. Essentially, it breaks the text down into smaller units. Tokens, they call them. These aren't always whole words, more like common chunks of characters that frequently appear together.
So instead of learning letter by letter, it's learning these recurring chunks, almost like recognizing patterns in the language.
You got it. And for this English to German data set, after byte pair encoding, their vocabulary, that's the set of all these tokens, ended up being about 37,000.
37,000, that's still a lot to keep track of, but I'm curious, did they always use this byte pair encoding? What about for other languages?
Good question. When they trained on English to French, they actually used a different data set, also from WMT 2014.
Okay, so different data, same basic task.
Right. But this French data set, it was even bigger, a whopping 36 million sentence pairs.
36 million, that's just, that's mind-boggling.
It is. And they also switched encoding schemes. They used something called word piece encoding this time.
Word piece, so similar idea, but breaks things down differently.
Exactly. The goal is still to find those common chunks. For the French data, they ended up with a vocabulary of about 32,000 tokens.
Okay, so different data sets, different encoding schemes, but the core transformer architecture, that's still the same, right? It's handling both tasks.
That's a key takeaway. The beauty of the transformer is its flexibility. Think of it like a universal language learner, just point it at the right data with the right encoding, and it can adapt.
That's really impressive, but all this learning, all these millions of sentences, that can't be easy on the computer, right? It must take some serious horsepower.
You're absolutely right. They needed some serious hardware for this. They trained their models on a machine with 8 NVIDIA P100 GPUs.
8 GPUs. Okay, now we're talking.
Those are some of the most powerful processors out there, specifically designed for this kind of AI workload.
Like having 8 brains working on the problem at once.
Kind of. And even with that much power, it still takes time. Their base models, for each step of training, it took about 0.4 seconds.
Each step, so there are many steps in the whole process.
Oh yeah, for the base models, they did 100,000 steps, which comes out to roughly 12 hours of training.
12 hours straight, even with 8 superbrains. So this isn't something you just whip up in an afternoon.
Definitely not. And they also trained some big models, even more complex ones. Those took about a second per step, and they trained them for 300,000 steps.
So let me get this straight. 300,000 steps at 1 second each. That's like over 3 days of constant training.
You got it. 3.5 days to be precise. It gives you a sense of the scale of this research, how much computation is involved.
It's mind-boggling. Okay, so they've got the data, they've got the hardware, but how do they actually make the model learn? Is it just a matter of feeding it the sentences and letting it go wild?
There's definitely more to it than that. They use a specific algorithm called the Atom Optimizer to manage the training process.
Atom Optimizer. Okay, that sounds like something out of a sci-fi movie.
It's all about efficiency. Think of it like a coach, helping the model make the most of its training time. It adjusts the model's parameters, those are like the knobs and dials controlling how it works, to make sure it learns as effectively as possible.
So it's like fine-tuning the AI's brain as it learns.
That's a good way to put it. And they also carefully control the learning rate, which is how quickly the model adjusts based on the data it sees. If it learns too fast, it can make mistakes. But if it learns too slow, it takes forever.
So it's all about finding that sweet spot, the right balance.
Exactly. And there's another crucial aspect of training. It's called regularization.
Regularization. All right, hit me with it. What's that all about?
Imagine you're studying for a test, right? And you just memorize the answers to the specific questions in the textbook.
Okay, I've been guilty of that a few times.
We all have. You might ace that specific test, but you haven't really learned the material. If you get a slightly different question, you're lost.
Right. It's about understanding the concept, not just memorizing the facts.
And it's the same with AI models. If a model just memorizes the training data, it won't be able to handle new data it's never seen before.
Ah, so regularization is like making sure the model actually learns the rules of the language, not just a bunch of specific examples.
Precisely. It's about generalization, making sure the model can apply what it's learned to new situations.
Okay, that makes sense. So how do they do this regularization thing? Do they give the model like pop quizzes or something?
Huh, not quite. They use a few clever techniques. One is called dropout.
Dropout? Okay, that sounds interesting.
It's a bit strange, but it works. During training, they randomly drop out some connections within the model.
Wait, they intentionally break parts of it as it's learning? That sounds counterproductive.
I know, right?
Eh?
But by doing this, it forces the model to learn more robustly. It can't rely too much on any single connection.
So it's like making a model work harder, become more adaptable.
Exactly. It's like training an athlete with weights on their ankles. They might struggle at first, but it makes them stronger overall.
Okay, I like that analogy. What other tricks do they have up their sleeves?
Another one is called label smoothing.
Label smoothing? That one's a bit harder to wrap my head around.
It's about preventing the model from being too overconfident in its predictions. We want the model to be right, but not overly certain.
So it's like encouraging a bit of humility.
You could say that. It's about being open to different possibilities, especially when encountering new information.
Okay, so it's like being a good learner, always questioning, always open to being wrong.
Exactly. And the final regularization technique they used is called length penalty.
Length penalty. Is that like punishing the model for writing sentences that are too long?
It's more about keeping the model's output in check. It's applied during beam search, which is a common technique for generating sequences of words, like when ChatGPT is writing a story or answering a question.
So beam search is like the AI figuring out the best way to string words together.
Exactly. And the length penalty prevents it from going overboard, writing super long or super short responses. It helps keep the output concise and relevant.
Ah, so it's like having a good editor, making sure the writing is just the right length, not too rambling or too abrupt.
That's a great way to put it. All these regularization techniques, they might seem counterintuitive, but they play a crucial role in making the model more reliable and effective.
Okay, so we've got the data, the hardware, the algorithms, and these regularization tricks. It sounds like they really threw everything but the kitchen sink at this problem.
They were meticulous, and all this effort paid off.
Yeah.
Their models achieved some truly impressive results, outperforming the previous state-of-the-art on several machine translation tasks.
Okay, give me the highlights. What kind of results are we talking about?
On the WMT 2014 English to German task, they got a BLEU score of 28.4.
The LEU score, that's got to be some way to measure how good the translation is, right?
That's right. It stands for Bilingual Evaluation Understudy, and it's a common metric in machine translation. The higher the score, the better the translation. And their 28.4 score, that was a significant improvement over the previous best result.
So, new architecture, better performance, that's already a win. What about the English to French task with that massive data set?
On that one, their big model, remember the one they trained for 3.5 days, that one got a BLEU score of 41.8. 41.0.
41.0, that sounds even better. Is that a big jump?
It was a major leap forward, especially considering that their training process was relatively efficient compared to some other state-of-the-art models.
So they're not just pushing the boundaries of accuracy, they're also doing it in a more efficient way.
Efficiency is key.
Yeah.
And the really interesting part is that they didn't just stop there. True scientists, they wanted to understand why the transformer worked so well, so they did all these experiments with different variations.
Okay, so they're tinkering with the model, trying to figure out what makes it tick.
Exactly. They tweaked things like the number of attention heads. Remember those multiple perspectives?
Yeah, right, like the detective team. So they were experimenting with the size of that team, seeing if more detectives always meant a better solution.
That's a great way to put it. And it turns out it's not that simple. They found that a single attention head actually performed much worse. But too many heads also led to a drop in quality.
So there's a sweet spot, a Goldilocks zone for the number of attention heads.
Exactly. It's not just about more is better, it's about finding the right balance. They also messed around with the attention key size.
Attention key, that's the part that helps the model figure out which information is important, right?
Yep. And they found that making the key size smaller actually hurt the model's performance.
Makes sense, right? It's like trying to pick a complex lock with a tiny key. You need the right tool for the job.
Perfect analogy. And of course, they also experimented with model size. As you might expect, bigger models with more parameters generally perform better.
More parameters, that's like more brain power for the AI.
Exactly. But they also found that those bigger models needed more regularization, specifically that dropout technique we talked about earlier.
Ah, so it's like the bigger the brain, the more important it is to stay humble, keep things in check.
Ah, that's a good way to think about it. They even experimented with the positional encoding, remember, the part that tells the model the order of the words.
Right, the map of the sentence. Did they find a better map?
They tried using a method where the model learns the positional encoding from the data itself, instead of using those fixed sine and cosine functions.
So instead of a pre-made map, they let the AI draw its own map.
That's the idea. But what's really interesting is that both methods, the learned embeddings and the sinusoidal ones, they actually produced almost identical results.
So it seems like both approaches can work well for encoding positional information. But if they both work, is there any reason to prefer one over the other?
The authors actually suggest that the sinusoidal approach might have a slight advantage
Oh, why is that?
because it might allow the model to handle sentences that are even longer than the ones it was trained on. It's like their map can extend further into unknown territory.
That's pretty cool. It's like they built a system that's not only good at what it knows, but also has the potential to handle even more complex language in the future.
Exactly. And that's one of the things that makes this research so exciting. It's not just about solving a specific problem. It's about laying the groundwork for future advancements.
Okay, so they explored the data sets, the training process, the hardware, those optimization and regularization techniques, even different model variations. It sounds like they left no stone unturned in their quest to understand the transformer.
They were incredibly thorough, and that's one of the reasons why this paper has had such a massive impact on the field of AI.
So they built a powerful model, they achieved groundbreaking results, and they documented it all in a way that allowed others to build upon their work.
That's the hallmark of great research. It's not just about the results themselves. It's about sharing the knowledge, inspiring others to push the boundaries even further.
And that brings us to the big question, right? What's the legacy of this work? How has the transformer, with its self-attention mechanism, changed the world of AI?
That's what I love about this field. There's always another layer to uncover. We've seen the technical details, but now it's time to zoom out and look at the big picture. Ready for that?
Absolutely. Lead the way.
Zooming out it is. We've spent a good amount of time looking at the nuts and bolts, the mechanics of the transformer. But the real story here, the lasting impact, it's much bigger than that.
Okay, I'm ready for the big picture. What's the lasting legacy of this "Attention is all you need" paper?
Well, think back to where we started. Before the transformer, the way AI processed language, it was very linear, one step at a time, very limited.
Yeah, like reading a sentence one word at a time, super slow and inefficient.
Exactly. But this paper, it threw that out the window, introduced self-attention, which is like being able to see the whole sentence at once,
Yeah.
grasp the connections, the context.
And it wasn't just a cool idea, it actually worked, right? The results they got, beating the previous best models, that was huge.
It was a game changer. Suddenly, AI could handle much longer sequences of information, understand the nuances of language in a way that was never possible before.
So it's like they went from a horse and buggy to a supersonic jet. in terms of processing power and understanding.
That's the analogy. And those shockwaves, they're still being felt throughout the AI world today.
Give me some examples. How has this one paper changed the landscape of AI that we see now, years later?
Well, look at the models that are everywhere these days, ChatGPT being the most famous example. Those are built on the foundation laid by this paper. The transformer architecture, with its self-attention at the core, it's everywhere.
Well, so it's not just an academic paper gathering dust on a shelf. It had a real-world impact. It spawned a whole generation of AI models.
It's like they planted a seed that grew into this massive, sprawling tree of AI advancements, and it's still growing, branching out in new directions.
Okay, so where are the most exciting branches growing? What areas of AI are being most impacted by this paper, even today?
One of the hottest areas is in making these models even more efficient. Remember we talked about those attention heads and how having too many could actually backfire?
Right, like having too many cooks in the kitchen, sometimes it's better to have a smaller, more focused team.
Exactly. And that's what researchers are working on, developing new ways to make self-attention more selective so it doesn't waste time on irrelevant information. Making these models faster, less computationally expensive, that's a big focus.
That makes sense, especially with these massive language models that require so much computing power. It's like optimizing the engine of that jet, making it even more powerful and fuel efficient.
Another exciting area is taking these ideas beyond language and applying them to other types of data. The authors themselves mentioned this in the paper, but now we're seeing it in action. People are using self-attention for images, for audio, even for video processing.
So from understanding words to understanding the world, visually, orally, that's a big leap.
It is. And the possibilities are endless. Imagine AI models that can analyze medical images to detect diseases, compose music that evokes specific emotions, or even create photorealistic 3D animations, all using the power of self-attention.
It's like this one concept, this idea of looking at the whole picture. It's unlocking entirely new levels of AI understanding and creativity. It's pretty amazing to think about.
It is. And that's why I think this attention is all you need paper is so significant. It wasn't just about building a better model. It was about fundamentally changing the way we think about how AI can process and understand information. It's a paradigm shift.
They rewrote the rule book for AI, so to speak, and the whole field is reaping the benefits.
Exactly. And it's a testament to the power of curiosity, of challenging assumptions, of pushing the boundaries of what we think is possible.
All right, so we've journeyed from the nitty-gritty details of the transformer to the far-reaching impact it's having on the world of AI, even years later.
And I hope our listeners are feeling inspired by the sheer ingenuity and potential of this field.
I know I am. So as we wrap up this deep dive, what's the key takeaway? What's the one message you want to leave our listeners with?
If there's one thing to remember, it's this. Don't be afraid to question assumptions, to think differently, to explore new ideas. That's how breakthroughs happen. That's how fields like AI evolve.
So to our listeners out there, stay curious, keep learning, and maybe, just maybe, you'll be the one to discover the next groundbreaking idea that changes the world.
Couldn't have said it better myself. Thanks for joining us on this deep dive.
Until next time.